It's a great honor for me to introduce the next speaker, Professor Guido De Philippis from CISA, Trieste. So I invite you all to welcome him with a round of applause.
Okay, thank you very much for the introduction. First of all, I would like to thank the committee who invited me and the local organizing committee for the organization of this big event, and all of you for coming here in this session. So what I will talk about is about the structure of measure which are constrained by a linear PDE and some of its application. And I'm actually very happy that I'm talking right now after the previous two talks, because somehow I will show you something which for us was a bit surprising. So how like harmonic analysis tools, which have been also introduced in the previous talk, are helpful in fields where they have not been used so far till now, like geometric measure theory and calculus of variation. So the general goal of the talk will be somehow to understand how will be the behavior of function or sequence of function which are constrained by a linear PDE. And so by behavior, I mean either possible oscillation or concentration of this function and sequence of functions. So the talk will be somehow split into two parts. The first part I will, so this is not a new argument somehow, so the first part I will review a bit what is known, and in the second part I will present the new results. So in the sense, what is known concerns oscillation, and what is new is what concerns concentrations. So let me start by fixing some notation, which will work throughout the whole talk. So again, I was talking about a linear PDE constraint. So A is just a linear differential operator of order K, which I'm taking homogeneous for simplicity. Most of what I'm going to say will work also for non-homogeneous operators. So alpha is a multi-index, D alpha is just a kth order derivative, and A alpha are constant matrices. Okay, so this operator takes vector-valued functions and gives you back vector-valued function. Okay, so this is the setting, and I will say that a function or a measure, or more in general a distribution, is A-free if it just solves A of u equals 0. So since A, as I was saying, is a constant coefficient differential operator, this is just classical definition in distribution. You just move everything on the test function. And this is our meaning. And what is important remark here, which I already stressed, is that this is actually a system. Okay, so this is a 0, which is a Rn0. So this is a system of n equations. Okay. Why one is interested in this type of things? There are several reasons. Let me start presenting two very broad ones, and then I will go more specifically as the talk goes on. So the first motivation is that a lot of natural differential operators are actually characterized by annihilating other differential operators. So the most classical example in this is probably the de Rham complex. So a form is exact. So it's the differential of some, so a K form, L form is the differential of some L minus 1 form, if and only if it is closed. Okay, I don't want to care about topology, so just say in Rn this is true. The second example is actually a particular case of this, which just tells you that if you have a distribution which it values into L times D matrices, well then this distribution is a gradient if and only if its curl vanishes. So this. And the third example, which is relevant in my talk and also in applications to elasticity, linear elasticity and plasticity, is the example of symmetrized gradient. So we will say that a distribution with values into symmetric matrices is a symmetrized gradient if and only if it satisfies the so-called Sylvenant's compatibility condition, which means that there is an operator which is second order and which is called Karl, which is 0. Okay, so it has to annihilate this linear operator. And you see that all of these are actually system of linear equations, okay? So these two are first order operators, while this is a second order operator. So the second motivation is actually, and here comes nonlinearity, because we can think that linear theory is somehow well understood, that most of nonlinear PDE can be taught as the coupling of a linear PDE and a pointwise constraint. So here there are just two examples, but there are actually many others. The first one is the example of conservation laws, so where you have a quantity which evolves accordingly to this conservation law, which is nonlinear. Well, then you can write this equation as the coupling of a linear constraint, so the divergence of my states in space-time is 0, together with the fact that V has to belong to the graph of U. And the second one is an even more classical example of semilinear equations. So divergence of ADU equals 0 is obviously equivalent to this linear system, divergence of Z equals 0, curl of V equals 0, together with this nonlinear coupling, okay? So, and this is, we'll see this as some interest later on. So now the question is how this differential constraint can influence the behavior of our solutions. So since the system is linear, we can use Fourier transform techniques to study it. So we just take the Fourier transform of A of U equals 0, and what we get is that the Fourier transform U hat psi of my solution as when you apply the symbol of the operator to this Fourier transform, you just get 0. Okay, so xi here will be the symbol of my operator. And just an important remark, this is, since I'm talking about system, this is a matrix, okay? So now, no. Now, I will say that an operator is elliptic if the kernel of the symbol is 0. So if this matrix is injective. And now you see that if you have an elliptic system, since the kernel of xi is 0 for all xi different from 0, so an important thing is that when xi is 0, everything degenerates here, so you can get information just when xi is non-zero. Then if you have a solution, then when xi is non-zero, this equation implies that u hat xi has to be 0, which just means that the support of u hat as a distribution has to be in the origin. So there are very few distributions which has this property, just basically is a finite dimensional set. So this gives you a very strong constraint on the behavior of your solution. So now what happens when the system is not elliptic? And here comes one of the greatest ideas of Murat and Tartar, which is to encode this loss of ellipticity into what is called a wave cone. So the wave cone is just the union among all frequencies which are non-zero of the kernel of the operator xi. And let me remark once more that this is a subset of the state space, okay? And this, in a sense, is what contains the amplitudes along which the systems fail to be elliptic. And this can be seen, for instance, in these two ways, which are both interesting. So the first one says that out of the definition, an amplitude lambda is in the wave cone if and only if there exists a non-zero xi, such that when you look to this particular type of functions, which are just taking values, which are basically depending on one direction, the one parallel to xi, and which are taking values along another direction, the one parallel to lambda, then this is A-free, no matter what is the function h you put here. So in a sense, you see that this should be related to the loss of ellipticity, because ellipticity gives you constraint on your solution, and here there is at all no constraint, okay? The second equivalent way to say is that the amplitude lambda is not in the wave cone, if and only if, when you restrict your operator to functions which just takes value in the direction parallel to lambda, so they are basically scalar-valued functions, well then the operator becomes elliptic, okay? So in this sense, the wave cone contains directions along which the operator is not elliptic. Let me remind, so you might think that this is related to what is called the wavefront set in microlocal analysis. Excitator is somehow related, but the wavefront set is something which lives in the domain space, while this thing is living in the target space. So there is when you look to system, the loss of ellipticity might not depend on the directions in the domain space, but also on the direction in the state space. Okay? So because of this loss of ellipticity, somehow we expect that the bad behavior of a sequence of functions, like I was saying, oscillation on concentration, they can only occur in the directions of the wave cone. And then it can happen that, since I was saying that a lot of nonlinear PDE can be seen as a coupling of a linear PDE together with a pointwise constraint, it can happen that the pointwise constraints prevents this fact, so prevents the state to take value into the wave cone, and now this can give you gaining of regularity, or if you want, of ellipticity. So this is just one example. So this system is at all not elliptic, because this is just curl of v equals 0, divergence of z equals 0. These are not two elliptic equations independently and coupled together. But once you add a pointwise constraint, if, for instance, your operator A is monotone, then you get an elliptic equation, and this gives you back regularity. Okay. So let me start talking about oscillation, and this is a well-established theory by now, and somehow well understood. So let's start with the sequence UK of functions which are all A-free, so they are all solving A of u equals 0, and which are weakly converging to some function u, which, since everything is linear and passes easily to the limit, will be A-free as well. So how can we pass from weak to strong convergence? Well, we see that weak convergence basically implies that the Fourier transform is pointwise converging. Okay, this is true if you ignore what happens at special infinity, just if you, for instance, put all the support of your sequence in a bounded set. This is just the back-dominated convergence theorem. And now you see that the failure of strong convergence, because of Plancherel theorem, is just the failure of this integral to go to 0. And this can just happen, since the sequence is pointwise converging to 0, just can happen if the mass wanders out at infinity. But now, since solving A of u equals 0 is the same thing that's asking that the Fourier transform of u belongs to the wave cone, this loss of mass can just happen in the directions of the wave cone. And so, for instance, two well-known but striking consequences of this fact, one is the theory of compensated compactness, which is due to Murat and Tartar, and there's several other applications, tells you that if you have a quadratic quantity which is well behaved on the wave cone, so on that part of the state space where you don't have control, then this quantity passes to the limit under weak L2 convergence, which is something you don't expect, because it's a quadratic quantity, so it's the product of two weakly converging sequences, which has no reason to pass to the limits. And probably the most known outcome of this theory is the Div-Car lemma of Murat and Tartar. And the second example is, in a sense, is a negative example. So if you now have a wave cone which is quite big, there are a lot of directions along which you can add oscillations. And maybe this oscillation will help you to saturate some pointwise constraint. And this is somehow what is behind the theory of convex integration. I cannot enter in further details, but just to mention that probably the first instance of this fact was the isometric embedding of Nash. Then it has been moved to elliptic systems by Müller and Schwerak and Zeghenidi. So here I'm putting elliptic in quotes, because for systems the notion of ellipticity is slightly more complicated in this setting, but I don't want to enter in. And probably one of the most striking outcome of this theorem is the solution of Onsager conjecture for the Euler equation, which was started by Delellis and Zeghenidi and then completed by Isach. So this is what I wanted to say about oscillation. So somehow this theory is well understood, or at least somehow classical. So what about concentration of solutions? So what do I mean by concentration? So let's take a sequence of A-free functions which are bounded in L1. Now, since you're bounded in L1, you cannot expect weak convergence in L1, because L1 is a bad space somehow. But what you get is weak convergence in the sense of Radon measures. So UK will weakly converge to some Radon measure mu, which will still solve my equation, because everything is linear, everything passes easily to the limit in the sense of distribution. And now my measure mu can be decomposed in an absolutely continuous part with respect to the Lebesgue measure, and in a singular part with respect to the Lebesgue measure. And somehow, the singular part should take into account the concentration of my sequence. So points where my sequence is going to plus infinity, which should be a null set somehow, but on which there should be still some integrals concentrating there. So now the question, which I want to address for the rest of the talk, is the following. So you have a measure, mu, which is a vector-valued Radon measures, which is A-free. So it's solving my A mu equal to 0. Now, what can we say about the singular part of mu? So let me, since we are talking about vector-valued measure, and this is somehow relevant, let me remind you that, okay, so the Radon-Nikodym theorem tells you that you can decompose, as I was saying, in an absolutely continuous part and in a singular part. And then another instance of the Radon-Nikodym theorem tells you that the singular part can be somehow always written in the following form. So there is a scalar-valued positive measure, which is this d mu s, so which is just the total variation of my measure, times some vectors, which is just of unique length, which is called polar vector, and which is in some sense taking into account the infinitesimal direction of my measure. And this is what will play a key role in the rest of the talk. Okay, so I was explaining you how this question is related somehow to the understanding of concentration, but there are a couple of other interesting applications of this of a possible answer to this question, and which are quite unrelated and surprisingly unrelated. So the first one is somehow the setting of linear Grove variational problems, when one is interested in minimizing some energy, which can depend either on the gradient or just on the symmetric part on the gradient. This type of energy are relevant in linear plasticity. And your energy density behaves linearly for large values of the entry. Okay? So these are what I'm calling linear Grove variational problem. And the second thing, looks to be completely unrelated, concerns the sharpness of Rademacher theorem. So let me remind you Rademacher theorem, which is a classical theorem in linear analysis, which tells you that every Lipschitz function is almost everywhere differentiable with respect to the, when almost everywhere is taken with respect to the Lebesgue measure. So this means that Lebesgue almost all points, you can find for a Lipschitz function a linear function which approximates my function better than to the first order. Okay? And now the question is, how special is the Lebesgue measure for this type of theorem? So in other words, what can I say about a measure, nu, which is just a positive measure in this set, for which every Lipschitz function is differentiable nu almost everywhere? And if you think one moment on this, you immediately see that this measure has to be somehow a bit diffuse, because, for instance, it's immediate to build an example of a Lipschitz function which is not differentiable in one point. So, for instance, your measure cannot be a delta, because if you put a delta in that point, then you won't get Rademacher theorem. So let me go a bit more deeply in these two applications. So let's start with a linear growth variational problem, and the easiest situation in which your energy depends on the full gradient. So we take a minimizing sequence, as we do when we want to minimize something, and because of the linear growth of W, the only bound we get is that the L1 norm of our gradients is bounded. But now, this means that my sequence of gradients, and actually of functions, will converge as a random measure to some gradients. And so the minimizer are to be studied in a natural way in this class of function of bounded variations, which are just those functions for which their distributional derivatives is a random measures. And now, to keep studying this problem, you need to understand the structure of measures which are gradients, which is the same, as I was saying at the beginning, to study the structure of measures which are card-free, right? And again, Rademacher theorem tells us we can decompose in an absolutely continuous part and in a singular part. And then, out of the work of Federer and Ambrosio and De Giorgi, we know that somehow we can decompose further the singular part into two parts, the jump parts and what is called the Cantor parts. So a way of thinking to BV function, in a very imprecise way, is to thinking them as a first approximation as piecewise C1 functions. So like the one I drew here. So this is a function which is somehow smooth, then there is possibly a jump, and then smooth again. And where there is the jumps, there is a singular part of my derivatives. But this is what is encoded in this jump part of the derivatives. But there are other examples, way worse, of BV function, and the most known one is the so-called Cantor function, which is a function which is almost everywhere differentiable with derivative 0, but which nevertheless it grows. So that it has to have a non-trivial distributional derivative, and this distributional derivative turns out to be a measure which is singular with respect to the Lebesgue measure. So you see that there is a quite precise structure here on the jump part of the derivatives, and in particular it is a rank 1 matrix, which is somehow telling us that the only possible discontinuities should asymptotically at least appear along one direction and takes value in another direction. And Ambrosio and De Giorgi in 1988, they conjectured that this is actually always the case, so that also the Cantor part will have this sort of rank 1 structure, and the way to write this properly is that the rank of the Rademacher derivative of the gradient with respect to its total variation has to be at most 1 at almost all singular points. This conjecture has been actually proved to be true by Giovanni Alberti in 1993, and is telling you, as I was saying, that singularities are somehow one-dimensional. Since it's proof, this theorem, which is known as one of the hardest theorems, I would say, in the theory of BV function, has a lot of application in the study of our relaxation and lower semi-continuity for the energies I was mentioning before, and also to the study of continuity equations with rough vector fields, which is basically the extension of Di Perna-Lyon's theory done by Ambrosio in the setting of BV function. And also now there is a very recent and striking result of Bianchini and Bottincato. Actually, this was known as a very hard theorem, but 2 years ago, a new proof of this theorem has been given by Annalisa Massaccesi and Davide Vittone, and it's actually a very short and precise proof, which is just 2 pages, which I would say is the proof from the book, just to quote Erdos. But both proofs really rely on some link between the structure, BV function and sets of finite perimeter, which I don't want to enter in. Okay, so let's move to the vectorial problems, which actually depends on the symmetric part of the gradient. And this time, as before, we have just a bound on the symmetric part of the gradient, so on the full gradient. And we see that, again, by abstract nonsense, our symmetric part of the gradient will weakly converge as measure to symmetric part of some gradient. And so these times minimizers should be looked at in the space of BD functions, so functions of bounded wave formation, for which is not that a full gradient is a measure, but just its symmetric part. Obviously, BV is a subset of BD, but it actually is a strict subset. Okay, this is due to the failure of Korn inequality. Now, if you take a function which turns out not just to be in BD, but also in BV, because of Alberti rank 1 structure, you see here that there is a very particular structure of its singular part. So it's quite natural to conjecture, and this conjecture has been around for a while, that this structure of the singular part should be true always for all BD functions. And this is somehow telling you that singularities should be the sum of two 1 plus 1-dimensional singularities. Okay? So this is for what concerns, just important, that as I was saying, to possibly answer to this conjecture, one actually has to understand the structure of measures which are symmetrized gradients. And as I was saying, this is equivalent to study measures which are car free, because these characterize symmetrized gradients. So what is instead the link of these questions with the differentiability of Lipschitz function? So as I was saying, every Lipschitz function is differentiable Lebesgue almost everywhere. So what about the converse? So the converse can be stated in two ways. One is the so-called weak converse of Rademacher Theorem, which tells you that every time you have a measure which is different, such that every Lipschitz function is differentiable nu almost everywhere with respect to this measure, well, then this measure has to be absolutely continuous with respect to the Lebesgue measure. Okay, so the converse is obvious. I mean, if you have a measure which is absolutely continuous with respect to the Lebesgue measure, then it satisfies Rademacher theorem. The strong converse is actually much more precise and tells you that every time you have a null set in RD, then you can find a Lipschitz function which takes value in some RL, this would play somehow a role, such that is not differentiable at any point of E. Okay? As the name suggests, the strong converse implies the weak converse. But nevertheless, also the weak converse would have a lot of interesting consequences. Let me list 3 of them. The first one is that we will answer to the top-dimensional version of Ambrosio-Kirchheim flat conjecture concerning metric currents, which I cannot enter too much in details here. This was observed by Gong and Schioppa. The second one is that this will actually provide a positive answer to the Cheeger conjecture about Lipschitz differentiability spaces. These are like metric measure spaces on which it's possible to develop a first-order calculus. And the third consequences concern the structure of measure in the so-called RCDKN spaces, which are like spaces which we will see in the talk of Ambrosio in 2 days. So I don't enter even in details, but it's somehow well known that weak converse of Rademacher theorem will have implication about these 3 problems. So what is known in this setting? The first result is that the strong converse is actually true in 1 dimension. And this is old results of the 40s. The second result I want to mention is that the strong converse is known in dimension 2. And this has been proved by Alberti, Cherney, and Price. And it tells you that every time you have a null set in R2, then this is contained in a non-differentiability set of a Lipschitz function going from R2 to R2. Okay? And why here there is an R2? Well, because there is an example of Price and then refine in dimension 2 and then refine in any dimension Price and Spite, that you can find a null set in RD such that every Lipschitz function which goes from RD to Rm with m which is strictly less than D is actually differentiable in at least 1 point of E. So to have a strong converse of Rademacher theorem, you really have to take maps going from RD to at least RD. And finally, in 2011, Cherney and Jones announced a proof of the strong converse of Rademacher theorem in any dimension, but as far as I know, the proof has not yet appeared. Okay, but what is the link of all of this with our original question of understanding the structure of measures which satisfy a differential constraint? The link comes from a very nice result of Giovanni Alberti and Andrea Marchese, which says that the weak converse of Rademacher theorem is equivalent to the following statement. So if you take a measure mu, which is matrix valued. Okay, so you have d vector valued measures, and that satisfies that the divergence of mu is 0, for instance, row-wise. So you have d vector valued measure with divergence 0. Then, when you look to the span given by the column of this matrix at singular point, well, then this span cannot be the full RD. So this statement is essentially equivalent to the weak converse of Rademacher theorem. I cannot give you this equivalence, but and it's quite surprising that is equivalent. But in a sense, what is very nice of this theorem, which is that understanding the weak converse of Rademacher theorem is the same that understanding the structure of divergence-free measures. Okay? So this was to motivate all the questions. So let me give you the answer to the question. So this is a result obtained in collaboration with Philip Rind a couple of years ago, and it tells you the following. So take a random measures, which is A-free. Then, when you look to its singular part, the polar of the singular part has to lie in the wave cone. In other words, accordingly to the heuristic I was presenting at the beginning of the talk, concentration can happen only in the direction of the wave cone. So before giving you some hints of how the proof of the theorem goes, let me give you a couple of corollaries. The first corollary is another proof of Albert-Rankin theorem, which is one line this time. Because once you compute what is the wave cone of the car, it just turns out to be done by metrics which are actually which are actually tensor products. So since we know that the polar has to belong to the wave cone, we get that at singular point, the gradient of a BV function has to be of rank 1. The second corollary concerns the structure of symmetrized gradients. I provide a positive answer to the conjecture I was presenting before. Indeed, again, the proof is one line. You just have to compute the wave cone of the car card, which is just an algebraic computation, which might take some time, I have to admit. But and it tells you that the wave cone of the car card is actually given by symmetrized tensor product. And the third corollary is that it gives a proof of the weak converse of Rademacher theorem and all of its corollaries. And why that? Because I was telling you that what we have actually to do is to understand the structure of measures which are matrix valued measure which has divergence free. But now by our theorem, these measures has to belong, the polar of this measure has to belong to the wave cone. But the wave cone of the divergence is just given by those metrics which has a non-zero element in the kernel, which means that the span of the column cannot be the whole RD. So I'm actually good in time, so I can give you some hints on the proof of this theorem. And I will start with a wrong proof, which contains, I think, the right ideas somehow, and which show you once more why this wave cone has to appear in this context. So let's start assuming that the theorem is false. So if the theorem is false, this means that the singular measure of those points for which the polar does not belong to the wave cone needs to have a positive measure. But now, you can somehow take a generic point in this set. Since it has positive measure, you have a lot of points. And this should be a point where, okay, the polar, which I called 0, as every generic point around. Okay, the polar does not have to belong to the wave cone. The second thing is that somehow around this point, the singular part of my measure is predominant, okay, with respect to the whole measure. So that the ratio between the singular measure of a ball and the full measure of the ball goes to 1 once you send the radius to 0. And now once you have a point like this, you can somehow zoom out around this point, as in my picture here. And what you get is that this measure, which is just my measure, zoomed somehow to scale 1, and normalized by the measure of the ball in such a way that we can see something of size 1 when we pass to the limits, well, then this measure will converge weakly to some measure which has a quite precise structure. First of all, what happens when you take a blow-up, since you are taking a generic point, you would expect that some continuity kicks in, and this continuity is read in the fact that the polar of this limiting measure is actually fixed, is constant, and is just the polar of my original measure at the origin. And the second thing is that, okay, and then there is a scalar part of my measure, which turns out to be, as I was saying, a positive measure, which is non-zero. And this is important. Okay, obviously, this measure will converge to something. What is important is to know that this something is also non-zero. This is, in general, non-true, but at generic point, it's actually true. And this is a theorem of price. Okay, so this is what we will get if we zoom in around the generic points. But now our equation is linear. We can pass to the limit easily, and we get that our limiting measure is actually solving the very same equation. But now if you take the Fourier transform, you see that you get that 0 has to be equal to the symbol of my operator applied to lambda. Recall lambda is a vector and the symbol is a matrix, times the Fourier transform of nu hat. But now lambda is not in the wavecon, which means that axi applied to lambda is different from 0 for all frequencies which are not 0. But now, as I was saying at the beginning, this implies that the support of nu has to be contained, actually, into 0. And not being 0 just because it's non-trivial. But now there are very few distributions whose Fourier transform is supported in 0, and in particular, they all come from measures which are absolutely continuous with respect to the Lebesgue measure. So we are zooming out around the point where the singular part was predominant, and we end up in something which is absolutely continuous. So we might think that this is not possible. Unfortunately, this is not the case. So this measure nu, which, by the way, belongs to the tangent, so what is called the tangent of my measures, which is just the set of all possible zooming around the point. So there are singular measures for which, so measures which are singular with respect to the Lebesgue, but when you perform this operation of zooming out, you will always get the Lebesgue measure. So this is not a contradiction to the fact that we were zooming around the point which was predominant for the singular part. In a sense, what we have shown till now is a strong rigidity result for a free measure of this particular form. But this rigidity result is not enough to conclude. So to conclude, we need to get a contradiction not at the limit, but just right before passing to the limit. So we have to somehow extend our rigidity result to a stability result. So we need to say that this was not possible just before passing to the limit. And how can we do this? Well, maybe because we can improve the convergence. So a priori the convergence was just weak in the sense of measure, but maybe it can be actually better. So this is not true generically for a measure. So what can give us hope for that? Well, once more, it's the regularization effect of ellipticity. So since we are somehow going in a point for which the polar is not in the wavecon, it means that somehow asymptotically our equation should become elliptic, and so maybe we can improve something. So let me just anticipate to you that, okay, well, most of you might know that ellipticity helps in improving convergence because you basically gain derivatives. Okay, here is not the case. It's not possible. I will show you why. But nevertheless, a tiny bit of ellipticity is enough to get our final contradiction. So let's go towards the new proof, the true proof of the theorem. So the first thing to do is somehow to fix the polar before passing to the limit. So a of mu j was 0. Now I can add on both sides a of lambda nu j, where nu j is just this time just the zooming of the scalar part of my measures. Okay? And what is good here is that what you have here inside the operator on the right-hand side is actually somehow going to 0 strongly in L1. This is not very deep fact. It's just a consequence of Lebesgue differentiation theorem. So this would not be possible if I just look to the directly to the limiting measure. This is possible because I'm just freezing the polar, not the whole measure. Okay? This is important. Now, what you can do is somehow, okay, I was a bit free in taking Fourier transforms here and there. If you want really to be rigorous, you have somehow to regularize and localize a bit things. But what you get now is that a of lambda uj, you should think uj to be basically nu j, is equal to a of sigma j, where sigma j is something which is actually going to 0 into L1, plus some remainder which this time is really well behaved. In a sense, there are less derivatives in this remainder than in the operator. And now you see why I was saying that you cannot hope to gain derivative, because here you have k derivative of a measure which are equal to k derivative of the measure. So even if you can cancel the operators, which is what ellipticity should allow us to do, well, you don't gain any derivatives. So you gain derivatives from this part, but not from these parts. And this is actually what you do. So you invert the operator and try to use elliptic estimates. So you can, remember, you can invert the operator because we are working in a situation where the operator is now elliptic, because I'm freezing the polar in the direction along which the operator is elliptic. Okay, so this term is actually nice, is well behaved, and here well behaved means that it's precompact in L1. Actually, you can show that you're even gaining derivatives, so this is really a well behaved term. Well, now, if you can really cancel the operator, these terms will go to 0 in L1, and now this guy will be precompact in L1 as well. But now, it turns out that harmonic analysis is not well behaved in L1, unfortunately. And, well, unfortunately or fortunately, I don't know, it makes things more interesting. But this guy is not going to 0 in L1, but is going to 0 in the weak L1 space. So that you need some other ingredient to conclude, and the important ingredient, which is somehow we borrow, it's a trick we borrowed from a paper of Allard, is that this quantity is actually positive. And now, when you have this structure of something positive, which can be written as the sum of something which is precompact in L1, plus something which is going to 0, for instance, pointwise, and also in distribution. It's not hard to see that this guy goes to 0 in distribution. Now you see that there is no room to compensation, because the negative part of this guy cannot, so the negative part of this guy cannot be too negative, because the sum of the two should be positive, and since somehow the average should be 0, neither the positive part can be too big. Okay? So this actually tells you that this guy is precompact in L1, and this is really the contradiction we were looking at, because these are measures, well, these are actually functions, but they are very, very close to our original measure, and our original measure was purely singular. And now, because of what I was showing before, is converged to something which is absolutely continuous, and now the convergence is not just weak in the sense of measure, but is strong in L1. And this is not possible unless the target measure is 0. And I was telling you that my target measure should not be the 0. Okay, so my last slide concerns some further work and some open problems concerning all of this question. The first one, which is one of my favorite one, is to understand more what should be the fine structure of a free measure. So for instance, I was showing you a very fine, refined structure for gradients, and now you can get also for symmetrized gradients. So what can you say about general A-free measure? What should be the typical dimension of a general A-free measures? And this is somehow we'll have some application. And it's something we are working on with Jonas Hirsch, which is a postdoc of mine, Philip, and Adolfo Arroyo Rabaza, which is a postdoc of Philip. The second question is, somehow I was explaining you that there is, ellipticity is playing a key role in all this theory, but actually when you deal with constant coefficients operator, a most refined notion is the notion of hypoellipticity. So it would be interesting to understand what if one can somehow reduce, give a definition of wave cone which is smaller, and get some more refined result in this sense, and also for varying coefficients, so which can have some application of Rademacher Theorem in Carnot groups. The other question concerns the family of extremal points of the set of A-free measures. So A-free measure is actually a convex set. So you can look for extremal points. And the fact that you know that any measure, any point in a convex set can be somehow written as an average of these extremal points is, in the case of divergence-free measures and of gradients, well known by the name of Smirnov decomposition and coarea decomposition. So the question is this peculiar of these operators? Can we extend this to other operators somehow? And one has to understand the structure of extremal points. And the last question, which is maybe my favorite one, is that if one can somehow improve what we have done to a sort of compensated concentration principle. In other words, for instance, an outcome of our theorem is that if you have a sequence of measures which are, for which the polar is not lying in the wave cone, or is lying at a fixed distance from the wave cone, these are actually L1 functions, not just measures. But is there an estimate on how much these functions are L1? So there is an estimate on their modulus of equiintegrability, for instance. So this seems to me to be a quite hard question on which we have some positive results, some counterexamples. So it's not totally clear to me, not even how to phrase this question, but I find it very fascinating. And I thank you very much.
Thank you so much for this beautiful talk. So I now have the pleasure to open the floor for questions. Yes, Carlos.
Sorry?
Is there any type of Orlich space estimate for the weak L1 part of your positive measure? Sort of as in Stefan Muller's work.
Well, but in principle, I don't know the remainder to be well behaved in any way, neither the transform. So I
just know the compactness for the remainder.
Yeah, I mean that part is somehow is bad. It gains regularity because the sum of it with something which is precompact in L1 is positive. So actually, that part can be in principle, and I think one can easily also build some example in which is as bad as any weak L1 functions somehow.
Okay, thank you.
Any other question? No? So let's thank the speaker again.